Now we're starting with concrete and masonry. First of all, dealing with masonry and brick masonry. After that, we'll move into stone and concrete masonry. So with brick masonry, we've got major projects such as this famous, the Great Wall of China, the Great Pyramids. And you say, is that masonry? Well, it might be considered what we call a masonry without any mortar, but it's still a masonry project of stone. There's stone and brick masonry that goes back a long, long time. It's one of the oldest building methods that we have in civilization. And in modern times, we use a lot of manufactured brick as part of masonry projects. So the key of modern masonry is mortar. We'll mix up a mortar mix that we lay the bricks or the blocks or the stone into. It's what binds them together. So what does mortar do? It cushions the masonry units, as you see in this first section, and then it seals the joints between the masonry units. It minimizes the flow of air and water through that wall of brick or stone masonry. It adheres the units. There's an adhesive property of the mortar where it actually binds or glues itself to the brick or the block or the stone. Now, a mortar mix sets up just like concrete does. It's not a concrete and mortar, neither one hardens by drying up. There's a chemical reaction with water. So you see the bullet down here at the bottom. We're looking at a second from the bottom. Mortar mix sets up just like concrete as a chemical reaction that we call hydration. We'll get more into those details when we get to concrete. But in mortar, it works the same way. We use Portland cement in the mortar, and it sets up by a chemical reaction with water. So just like concrete, you got to keep protected from freezing in cold weather. Not as much of a problem in Louisiana, but if the mortar freezes, the water will expand while the concrete is trying to set, while the mortar is trying to set up and expand and break up the mortar. So you got to protect it from freezing in the same way that you do with concrete, and you have to keep it from drying out, which is particularly a problem in a really dry climate or a very hot climate where things evaporate more quickly. And so we have to combat those things as we're laying bricks and blocks and stone into mortar. So, combination with the brick, the mortar contributes to the appearance of the wall. And of course, the pattern of the brick that you use matters. And so you're seeing various patterns in here and various thicknesses of mortar. Now, the standard mortar thickness of these joints, and the most common by far, is a 3/8 of an inch wide mortar joint. So that's something you need to know as a test question. It'll show up as a test question near you at some point. So first of all, the ingredients of mortar. We basically have the Portland cement, the hydrated lime that's mixed into the Portland cement, and that's what makes up masonry cement. But anyways, those two ingredients, the cement, the lime, and then there's the gravel and the sand. Well, no, there's no gravel. There's sand. I'm sorry. Okay. So he's talking about concrete lately. But fine aggregate, which we call sand, is a fancy name for sand is fine aggregate, and water. So let me back up. Portland cement, the hydrated lime, the sand, and the water. Now, when you're looking on this page, yeah, you see masonry cement. Well, masonry cement already has the lime mixed into it. And so if you buy a bag of masonry cement, it already has the lime. Remember that the cement is not the same thing as the mortar mix. The mortar mix, when you buy a bag of a mortar mix, it has the sand already in there with it, and then you just add water. And so it's very, very common in mortar mixes to do everything in a kind of a volumetric measurement where we measure the volumes of these ingredients. Whereas when modern concrete at a ready-mix plant, we weigh the ingredients of a concrete mix, we don't measure the volume of them so much. But if you were mixing concrete by hand, then volume is all you've got, and then the amount of water that you need to get the consistency that you need. But, in a modern concrete mix at a ready-mix plant, they're measuring these ingredients much more precisely than that. The other thing you'll see on these two bags on the left, bottom left, there's two bags of masonry cement premix. Just the cement, no sand, but it says type M on the top bag. It's kind of covered up by the bottom bag, type S. So there are different types of masonry cement. Type S, type M is the strongest, type S maybe the most common. Then there's N, O, and K. And I'll get back to that on a table in a minute. But the only difference between these different types is the amount of hydrated lime added to the mix. The more hydrated lime you add, the weaker the mortar becomes, but it gets more workability, which is also valuable. And so you want a kind of a balance in there. But it depends on what you need. If you need very strong mortar, then you might be going with type M. Probably most commonly we use type S. And if you're dealing with interior masonry where you're not dealing with the weather, cold or hot, particularly cold weather, freeze-thaw cycles and such, then you might be, if you don't have to worry about that, then you might be able to use type N. Okay, the cement is the same cement that we use in concrete mixes, and we'll talk more about that when we get to the concrete area, but the Portland cement, the same type of type 1 Portland cement that we use in almost all concrete mixes. Most of them anyways, maybe 90% of them is type 1 normal cement, and that's the same stuff we use in this mortar mix. The hydrated lime looks powdery just like, even though they say it's hydrated, which means they've added water in some way, but they've added water at temperature, so it's a little different. It's still a powder, so it doesn't mean too much. The hydrated lime, there's quicklime, there's hydrated lime. The hydrated lime is easier on the skin and more stable, so they don't use a lot of quicklime. They mostly use hydrated lime. And again, what does the lime do? It adds workability. So you see this hydrated lime is added to Portland cement to make masonry cement. You see that at the top right-hand column here, that top bullet. The one below it, lime imparts smoothness and a workability, kind of the same thing, in the mortar. So that's what it's there for. One other thing that it does, though, is it helps to retain water and keep the mortar from drying out so quickly. So it has maybe another benefit too. Okay, the sand that we use is a well-graded engineered sand called a masonry sand. So it's not just any old beach sand. It's very specifically particle size going from a fairly large sand granule down to a very small granule. So it has to be well graded from large, medium, and small sand particles, free from contaminants. You don't want it to be chemically active with sulfates and such in the sand. No salt. Salt will chemically react and cause the mortar to set up more quickly, and it'll also cause problems with corrosion of mesh and rebar that could be in contact with the mortar. Okay, and then we add the water. If you can drink the water, you can certainly use it to mix in the mortar mix or a concrete mix, but it doesn't have to be as perfect. But you really, really don't want to use seawater or salty water. So even the brine water that we have in the Lake Pontchartrain wouldn't be a wise idea. So on a typical masonry job site, they are mixing it not in a wheelbarrow like this guy on the bottom left is doing that. If you had a small batch, you might do that. But more often they'll use one of these mortar mixers that has a horizontal shaft with paddles inside it. This is a little bit different than the typical portable concrete mixer, which is more of a drum like a ready-mix truck. But anyways, and they're counting the number of shovelfuls, and so they might have 3 parts or 2.5 parts sand to 1 part cement, masonry cement to maybe a 1/2 part water or something like that. They'll have a certain number of volume shovelfuls or bucketfuls or something that they use as a system to make sure you're having a consistent mortar mix. And you don't want to mix up too much at a time because it sets up, and so they're forever making more mortar, throughout the day, because the mortar is setting up. As soon as you mix water with it, the chemical reaction starts, and they've got to make sure they've put it to use, or else they throw it out. So you're better off to throw out mortar if it's setting up too quickly. The mortar mix has basically the same volume of sand as the overall volume of the mortar, because what happens as you mix these ingredients with the sand, the Portland cement and the water, you're just filling the voids between the sand particles. And so there's basically a cubic foot of sand in a cubic foot of mortar, basically. So when you're trying to figure out if you can figure out how many cubic feet of mortar you might need, which we sometimes do with calculations either manually or with tables, then once you know that, then you know how much sand you need to have on the job site, plus some extra, of course, for waste. And there tends to be a fair amount of waste with mortar, because it sets up before you get finished. You got to chuck it out and just start over. I mean, make a new mix. So again, as I got in bullet form, the second from the bottom, lime improves the workability of the mortar. So it's a very important ingredient in mortar. Okay, so I've got a couple of tables here, but I probably could ignore this one. I want to get to another table coming up here soon. Let's see, I think it's coming up. Oh, after this page. Well, let me look at this page first. Anything besides these ingredients I've been talking about, the sand, the Portland cement, the hydrated lime, which of course the two of those, the lime and the cement mixed together make the masonry cement, and the water. Anything besides those basic ingredients is considered an admixture, whether you're adding color to the mortar to give a certain color to the mortar. Sometimes there's pigment added. There can be bond enhancers that help it bond better to the brick or the block. There can be set accelerators that help speed up the set of the concrete, and there's set retarders that slow down the set. So in cold weather, you want it to set up more quickly. In hot weather, you want it to set up more slowly, so sometimes they'll have additives for that. And there can be additives that are added to help the mortar be more water repellent right in the mix. And there are workability enhancers. Well, there already is the hydrated lime, which is not considered an admixture with mortar. It is if you're adding it to a concrete mix, though. But there's other kinds of similar supplementary cementitious materials, how do you like that combination of words, that we might add that are kind of like hydrated lime that could also be added. Okay, so now finally, this is the page I was looking for. The mortar types. I mentioned that there's M and S. We saw those on the bags. So M gives you the highest strength mortar, less lime. So there's more of the fine material is just this cement. But so there's that. And then but it's harder to work with, but it gives you the highest strength. The next strongest mortar mix would use type S masonry cement, which would have more hydrated lime. And so, yeah, in load-bearing masonry, type M and S are used for load-bearing masonry, where they're actually taking the loads of the building and such. And of course, if there's another kind of load besides sheer weight of the building on the wall or whatever you're talking about, is wind loads, and there can be seismic forces. And seismic forces, we're talking about earthquakes. Not really a problem in Louisiana so much. Type N is N for non-load bearing, I guess you'd say. But certainly is it can be on exterior masonry if you're not subjected to severe lateral loads and not extreme weather environments such as freeze-thaw cycles of winter. We don't have a lot of freeze-thaw cycles in Louisiana, so that's part of so it's more likely that you're going to find N used in a wall that's inside the building, out of the weather completely. So a brick wall that's part of a fireplace, or maybe some other brickwork that you might have inside a building, could be type N, whereas outdoors and for load bearing, you're generally going to be probably using type S. And maybe if you really need some strength and durability, you might be going with type M. Down there at the bottom, the last two are the O and K, and OK stands for OK. No, O, well, the K stands for crappy. Okay, did I say that out loud? Okay, well, it's really the lousiest. It's got more hydrated lime than cement in the mix, and so it's a very white, chalky mortar. And you'll find that in old historic buildings. And same thing with O. There's less hydrated lime in O than there is in N, but K has the least amount of cement and most amount of hydrated lime. And so it gets to the point where you can literally take a little pocket knife and carve through the type K mortar. It's just that bad. So you say, well, why would we ever use it? Well, the thing is, when you are talking about a historic, well, first of all, the reason they used it is because cement was way more expensive back when old historic buildings were being built. And so they were saving money. That's the bottom line. They didn't just invent cheap contractors. They've existed from the beginning of time. But the reason in modern times that you would still need to mix type O or type K mortar, even though it's inferior to the mortars we use in modern construction, is for historic restorations, because you cannot use a stronger mortar when you go and add more mortar into some joints that are there. Sometimes we have to grind out the existing mortar enough to go and replace it with some that's maybe damaged or fallen apart and deteriorated to the point where you got to carve it out or grind it out of the joints and chisel it out and then repoint it, as we say, put more mortar in there. You don't want to put stronger mortar on the outside of those joints or on the exterior part, because the walls flex in the wind and there's movement. You don't really understand, we don't see it very easily, but the walls are moving around all the time in the wind. And that flexing can literally shear off the front faces of the brick and ruin your old historic wall, So you got to match with similar quality mortar, type O or type K. So you have to determine how strong your mortar is ahead of time and try to figure out what mix is going to be what you'll need, how much hydrated lime you're going to need for that historic restoration. So old historic buildings, when they're being restored, that's big money. So specializing in that kind of construction is not a bad idea. It's just almost always those kinds of things involved needing special kinds of money for that kind of a restoration of some important landmark or a building of some kind. Anyways, the MSNOK, you can remember it way down here at the bottom right corner. It says designations for mortar type in decreasing order of strength come from every other letter in the phrase mason work. So you see mason work down there where I've capitalized the letters MASONWORK, and that helps you remember this order. It's just a trick, really, but anyways, it's something to consider. But remember that M is the strongest and K is the weakest. S is the most common, and in some statements they would say S and N are the most common, and that's what it says down here at the bottom of the left-hand side of this page. Type S and type N mortars are the most common. So you might see a test question about that too. Okay, here are some mixed designs, basically just talking about by parts. And it's very, very common with volumetric mixed designs of concrete to refer to them by parts. And so if your part is a shovelful, then yeah, you're talking about one part would be one shovelful, and a quarter part by hydrated lime, and maybe the sand. The range would depend on circumstances, whether it's going to be 2 1/4 to up to 3 parts or 3 shovelfuls of sand, and then the amount of water that you need for the consistency that you need. And there's a bunch of other, type M, S, and N mixed designs on this table, but it's just kind of an interesting thing. More than else, I'm not making you memorize that. But if I was ever to ask you what is the primary ingredient that we have the most of in any mortar mix, it's going to be the sand. Just like if we were talking about concrete mixes, the gravel and the sand are the most plentiful ingredient by volume and by weight. And actually, specifically when you're talking about a concrete mix, it's going to be the gravel. There's going to be more gravel than there'll be sand. There'll be more sand than there'll be cement. There'll be more cement than there is water. And there, so that by order of volume or weight, you know, the aggregates take up more volume, and then you fill those voids with the sand, with the masonry cement, and then you add the water to get the consistency. Um, the strengths of mortar. The strongest stuff they've got here on this table is 2,500 psi. PSI stands for pounds per square inch. So PSI, pretty common measurement. You may have seen it in other places like tire pressure. PSI, you talk about, I don't know, 35, 40, 80 PSI, depending on what kind of tire you have. Here we're talking about a compressor strength of 2,500 for the Type M, 1,800 for Type S. So that sounds pretty impressive when you're thinking about tire pressure, but when it comes to concrete, these are pretty wimpy numbers. You know, the pretty much the most common, boring, plain vanilla concrete that you're ever going to deal with is going to be for regular concrete for foundations and stuff will be 3 to 4,000 psi. And then when you get to a higher strength, maybe 5,000, and with precast bridge girders and stuff, we're looking at 6, 7, sometimes 8,000 psi. Here, the Type M is not too bad at 2,500, still pretty weak. Type S is kind of pathetic compared to concrete, and when you get down to N and O and K, we're looking at embarrassing numbers for strength. Not very strong at all. And you see the metric equivalent next to that in megapascals. And these are strengths calculated normally, and this is what we do with concrete and masonry. We calculate these strengths, generally after 28 days of curing from the time that mortar was mixed. So when we're talking about brick masonry here and laying these brick walls, and first of all, we're looking at the brick. The brick itself is made of clay. Well, you kind of knew that already, right? So literally they take natural clays that are excavated from the earth. They try to find good quality, pure sources. And if you're trying to make a whole bunch of red brick, maybe the most common color of brick would be red. Well, you're going to a source where there's a lot of iron in the soil. And so iron, well, we know about steel and how shiny it can be when it's, clean steel. But once it has a chance to oxidize, to rust, it turns red. So we know about red rust. You can see, though, all that red that we're looking at in this picture, that's iron. And so iron is the big big thing that drives the color of red brick, which is really, really common. So they'll go and purify and screen the particle sizes, and add some water to achieve kind of a plastic mix of clay. And ultimately they end up with a nice pure clay that's all very consistent and then ground down to particle size that you needed, all mixed into a big goo, a big batch. And eventually you make bricks with it. So modern brick is typically done like this brick is. It's called what we call an extruded brick or a stiff mud process. So if you remember anything about playing with Play-Doh or clay or something in your youth, you may have had if you had a deluxe Play-Doh kit, you could actually squish the brick through a shape to make a star-shaped snake or something. Well, that would be extruding. And so that's what happens with brick is it's literally squeezed out through a form to give you the shape. And they'll just literally squeeze out a big flat sheet of brick that then gets sliced with wires to cut it into literally the bricks that we know about today, So that's the extruded brick. And this is about 90% of the brick in this country is made that way. In an extruded bricks process or a stiff mud process, it may mean the same thing. Meanwhile, a lot of old-fashioned brick, and some brick that's made today still is made through a soft mud process where you need a form and you squish the softer mud into a form to make the shape of the brick, and then you pull the form away and leave the brick behind and then bring it to the oven. Or that's the thing about brick is it can be made in a much simpler way where you just dry it out in the sun, in hot sun. And so across the world, and from the beginnings of time, you could take a good quality clay or some lousy mud, and one way or the other, maybe mix some straw with it and anything else. You could make some kind of a brick that you let out, dry out, and then you can go and start building with it. And so, it's a simple, it can be a very simple, low technology thing that you're building, but around the world, especially in hot climates, having a bunch of stone or brick that you build a building out of tends to store the temperature, the average temperature, which can be really helpful because at in places that are hot, they can often, a lot of those desert kind of places will cool off at night and then heat up during the day. And if you got this building with this massive thermal mass of all this brick or concrete or stonework, it stores the temperature, the average temperature, so that it makes the building cooler during the day than it would otherwise be in other places out in the heat. And at night, it's kind of storing the warmer temperature too, and so it means that it's less cold inside inside that building at night when temperature drops. So it's just it's a pretty practical building material. And in modern building, of course, bricklayers with all the equipment, the scaffolding and the big articulating four-wheel drive forklifts and everything we've got, it makes for a fairly efficient system. Okay, I'm getting carried away here. Let's just get past this now. Yeah, so most modern brick is run through a kiln and through an oven where it's baked. And so here we've got a very common thing on a high production brick manufacturing thing is they've got a tunnel kiln where they literally have a track that this cart is going through, and they can keep running another one right behind the other, and it goes through slowly through the oven, maybe taking from 10 to 40 hours, depending on circumstances, what they're trying to make or what kind of brick or clay they're dealing with. And just like, when you're cooking buns or bread or something in an oven, things will tend to brown a little differently in some places. So the brick will literally change color differently depending on its orientation in there. Anyway, so now looking at the brick sizes, there's a whole bunch of brick sizes out there. There's a lot to say about that, I suppose, but I want to just focus on the fact that most brick is roughly 8 inches long. So this very top line is a pretty good common thing of bricks, whereas modular size, the very top line where it says 4 inches by 2 2/3 inches by 8 inches. But that's the nominal numbers, in the same way that when I was talking about 2x4s, a 2-inch by 4-inch board, a 2x4, they lie. It's not, that's the nominal number. That's the rounded up number. The actual size of a 2x4 is 1.5 by 3.5 inches. Well, it's the same with brick. So you see that top line, the very top line is just running across under modular. And when you get over to the right-hand side where I've got actual dimensions, so the actual width of a brick in the wall, the thickness of the wall when you lay the brick in the way, would be about 3 5/8. The actual height is about 2 1/4 inches, not 2 3/3, and the length of that brick, instead of being 8 inches, is more like 7 5/8. Well, what happens is by the time you install it in the wall, including the mortar, then you get the nominal dimensions. We were looking over at the left-hand side. So, yeah, you get a brick that's 7 5/8 long, 7 5/8 of an inch long, horizontally in the wall. With the mortar joint, it is 8 inches with the standard 3/8 of an inch mortar joint. So 0.375 of an inch. So anyways, when you add that all together, you get your 8 inches. And the same thing with the height. You end up getting about 3 bricks equaling about 8 inches. And so you can literally count the bricks and figure out how tall a wall is sometimes. If you can't stand a measuring tape up, you can often carefully count the bricks to get back at a little bit of a distance and such. And then there's other sizes. There are some 12-inch brick, but the reality is that, that it's rounded up to 12 inches when it's installed. And there's even some 16-inch brick. So there are some specialty brick out there, but the vast majority of it is 8 inches long. And you get roughly a 4-inch thick wall of brick. Very, very, very common. That said, you can have two thicknesses together, two widths of brick, and that would, two thick a 2 width wall would be an 8-inch thick wall of brick, kind of thing. Okay, so let me skip across here. There's some specialty shapes of brick too. Here I'm kind of showing a picture from looking out a window in Louisiana building over towards the Cypress building, but you see how they've got a cap on top of that wall. They've got a sloped brick with yeah, I've got trouble with finding my cursor in this video, but anyways, but yeah, those details, they cost money. You're going to figure out how many bricks you need by looking at how many square feet of wall you have and how many brick you can install in per square foot and that sort of thing. But when you're talking about the detailed brick, specialty brick, you're going to be figuring out how many linear feet of brick you're going to have across the top of that wall for that. Now, we also talk about brick in terms of how solid it is. So solid brick is considered not less than 75% solid in any slice through that brick. And so both of these sample types of bricks on this page are considered solid. That one, that's soft mud process brick over here on the right, upper right, it has a bit of a hollow cavity there, but as a percentage of the whole brick, it's basically considered solid. They call it a frogged brick when it's like that. I guess presumably you can put it over top of a little frog and trap it there, I guess. I don't know. That's my understanding. And then there's hollow brick. And so hollow brick is mostly hollow as opposed to mostly solid. So hollow brick, anything less than 75% solid to up to 60% hollow. So when we start looking at concrete masonry block in terms of brick or block, and that's really what these pictures are showing is concrete masonry block, it's in that sense, that's hollow brick. These standard concrete masonry units, CMUs. CMU stands for concrete masonry unit. Those blocks, some people nickname them as cinder blocks because we did add coal ash to them and other kinds of cinders as a supplementary cementitious material. But in hollow brick, it gives you space, and what makes that structurally sound is that you use those hollow areas in order to pour concrete and rebar, place rebar and concrete inside those cells to make it a much stronger system. Now, there's facing brick and building brick. So the facing brick has a nice face to it, right? Facing bricks are pretty. The brick you're looking at here, some people, its beauty is always in the eyes of the beholder, but this brick is not considered facing brick. It's considered building brick, meaning, yeah, you can build a wall with it. It just may not be very pretty. And so say, well, why would we even do that? Why would we use junky brick like that? Because you can use less expensive brick that didn't work out so pretty that they could easily sell, to make a firewall. So a lot of older buildings in particular were built with firewalls dividing up the building into sections, to keep the fire from spreading. And they would use brick that wasn't pretty because it was never going to be seen. Once it was installed, it would be hidden inside behind some drywall or something, and plaster or whatever. Okay. There are also different brick grades. And by brick grades, we're talking about how porous is the brick. So a brick that's not very porous can be used effectively in cold, moist environments where you get a lot of freeze-thaw cycles. So the dark shaded parts on this map are showing areas where they tend to have very regular freeze-thaw cycles throughout their winter. And so it means that you might get some sun during the day that thaws out everything, and then you might get some rain at some point that later that day that goes and soaks into the brick, and then it freezes at night and starts breaking up the brick. So that's what we're trying to combat. So the bricklayers will literally one of the ways they tell what kind of brick they've got is to spit on the brick and time how long it takes for that gob of spit to disappear by soaking into the brick. So when we look at the three different categories, there's severe weathering brick, or SW for severe weathering. There's moderate weathering brick. That would be a lighter shade in this diagram here, or MW. And then the lightest area down there along the southern border here of the states, we're looking at negligible weathering brick. So NW. And so over on this table here, you can see grade SW for severe weathering down at the bottom or at the top. Either way, I've got it described here, MW and NW. So, it's severe, moderate, and negligible. And so you just kind of want to remember those categories enough so that you can answer a question about that. So you can use negligible weathering in places where you're not going to get in interior applications where the brick is not going to be getting soaked. In Louisiana, we don't have the freeze-thaw cycles so much, but we do have trouble with, every now and then, not as often as in many other areas, but where we can get rain all day. And when we get a lot of rain that soaks into the brick, it can migrate in and start causing mold troubles and stuff. And so it still is not a good idea to be using negligible weathering brick here, even though we don't get a lot of freeze-thaw cycles, because there's other reasons. It's the mold that can grow, the water that can get in and cause damage or attract termites and that sort of thing. I mean, not that the termites will eat brick, but if the water is getting in past the brick, it might be getting to some wood framing or something of that nature, or rusting some steel studs or that sort of thing. So brick grade can be important. Watch for it in your specifications on drawings to make sure you're not ordering a brick that's not appropriate, because that can get you in legal trouble. There's also brick type, which has to do with the uniformity of the brick itself, and so I'm not going to test you on this, but there's a couple of classifications for brick to be aware of. So now I'm moving on to talk about some brick terminology. Every level of brick horizontal level of brick that you put, every row that you put into a brick wall is considered a course. So if you're counting how many bricks high a wall is, you're counting how many courses there are of brick. So that's that first term here. Now then the second term is looking at the mortar itself. So a horizontal mortar row, or a joint full of mortar, we call that a bed joint. And if you think about when you sleep in a bed, the bed is horizontal normally. Then you're laying the brick into a bed of mortar, so it's a bed joint. As opposed to the mortar in between two bricks, the vertical mortar joint between two bricks, that's called a head joint. And partly that comes from the fact that the end of the brick like that is considered the head of the brick. So now this next page, never forgot about this one. This is looking at something I've already mentioned a little bit earlier about the width of brick, or the wythe. I'm never quite sure which way to pronounce that. I think most places in the country would pronounce it the wythe. How many wythes? Sound like you have a speech impediment when you say it, but how many wythes does this wall have? Wife? No, wythe. TH. Okay, so WYTHE. So each vertical column or stack of bricks in a wall is considered a wythe. So this wall that we're looking at a cross section of is a 2-wythe wall. And then the mortar joint in between those walls is considered a collar joint. So some of these terminologies cross over from various framing and other terms we've looked at. That we talk about the wood that we put up in an attic between two rafters near the top. And that kind of joins the two together, near the top at least, of the rafters. So as in wood framing of roofs, so collar joints or collared collars and that sort of thing are joining things together. And so that's what this is for. But here's a more important picture. It's showing several terms that are important. And I've got a better page coming up after this that kind of summarizes all of them. But this is a good picture to look at. So let's look at the second one on this list, the stretcher. The stretcher, you're laying the bricks in their normal configuration where, as let's say it's let's say 1 1/4 or 2 1/4 inches tall. And so that's the height that you see in there. So they're sticking out of that brick, for that row. That's the normal configuration of a brick. And the 4-inch width of that brick is part of the width of that wall, the horizontal width of the wall in there. And of course, running 8 inches. So that's a common running bond when you have a brick like that. But anyways, it's considered the stretcher configuration, which is the most common. When you go down to the next bullet down below there, you'll see I'm pointing to a row of bricks where you're just seeing the end of the brick poking out. That's considered the header configuration. That brick is now in the header configuration. And so the idea is if it was a 2-wythe wall, then you could have brick that is spanning from one wall to the other. And out of that, you end up with this header configuration. So that's traditionally what that has meant. But sometimes we actually build walls where there's just one thickness of brick for the whole wall. And so then you just got a little piece of brick there turned around the other way to make it kind of simulate a bunch of headers, and they're actually just part of the decoration of the whole thing. But in theory, it's kind of like another kind of way of having a collar in there that's joining the two different brick walls together with a brick that's spanning from one to the other. Now down at the very bottom, we've got the soldier. And a soldier is having the same face exposed that we've seen on the stretcher. It's still that way, but they've rotated it, standing it upright. So we're still looking at the pretty face of the brick exposed, the same face is exposed at the stretcher row, but it's standing up at attention like a soldier would. Okay? Brick laid on its end with this face, the nice face, the shorter face really showing up. Now, the sailor is not shown here, but the sailor would also be standing at attention like this, but it would be turned with its chubby face out. So I always remember which one is which by thinking about the sailor sitting around on a boat all day getting fat. Okay, any sailors in here, they're going to come and punch me in the nose. No, but I just think it's good to remember stupid things sometimes that help you remember the difference between a soldier configuration and a sailor configuration. And on this page right here, I can get it to active, you're looking at some drawings that kind of show you these orientations and maybe a bit of a study guide here that can help. For the soldier and the sailor configuration over on the right, every row is one course of brick. Now, when you got a whole wall and another wall, each one of those walls is considered a wythe. So then if you got the 2-row wall, that's a 2-wythe wall. So you get the idea. The header configuration, when it's joining two walls together over here, gives you that kind of consistency too. The stretcher, on and on. Okay. Beyond brick, we'll sometimes, if you got a 2-wythe wall of brick, we'll join them at the top maybe with headers that are running across, or sometimes every so often through the wall we could have some headers that are helping to join them together. Well, there's different patterns out there for brick, and so they have names to them. So here, a common running bond, or sometimes just called the running bond, just has what the stereotypical thing we see in brick where, every new row is going to be halfway over the pattern of the row below it, so that when you're at the center of that brick, that's where you find the joint. So, that's the running bond. So these have names, and they could show up on a job that you've got to bid, and you need to pay attention if they've got anything other than running bond. Anything else is going to be a little complex, and that means more labor, more time, more money. So you just want to make sure if they have specified, I'm using the word common running bond, but a little c common, but the one down below it is called a common bond, and it actually has every so often a header row, maybe every 5 or 6 courses. So they're kind of doing that there. Then there's the English bond, and the Fleming bond. So those are all common ones. There's a bunch of others out there. And so when you're reading the specifications and bidding a job, this is where you need to know these kind of things enough to go and make sure that your masonry contractor that's giving you a subcontractor or a bid for a job, that they paid attention to that, so that you end up not underbidding a job because you got, a too low ball of a bid, We tend to lay out buildings with brick and block in 8-inch increments, because the bricks installed and the blocks installed all kind of end up having these units or partial units of 8 inches. And so our windows and our doors tend to be divisible. The width, the rough opening for a window or a door should be tied to being some multiple of 8 inches. And so it happens a lot in our industry. We start off by establishing the corners of a building in brick or block. And so as we finish establishing those corner leads, we get that done. You establish those corners first, and that means you're going to have your senior mason doing that kind of work, the higher skill part of establishing those corners. And then the other masons will be filling in between. Now you're looking down here, they use a lot of string lines to try to keep this wall straight. It's amazing how close they're able to get it, but they basically spend their whole time adjusting and readjusting as they've built up these walls. And then once you've laid it into a bed of mortar, you've got to tool that joint on the outside of the wall so that you don't end up with a blob sticking out like we did basically in this picture, these pictures down at the bottom of this page. And so, yeah, they can scrape off the excess, but they come back and tool the joint to smooth it out enough so that you don't have it quite as porous of a joint as you otherwise would. And you don't want any mortar sticking out where the rain can land on it and find its way in there. So there's certain joints that make more sense than others. There's the second one from the top over on the right-hand side is called, the second one from the right is from the top really, is the concave joint. And so the concave joint and then the one below it, the V joint, are the most common used for exterior applications where they worry about moisture soaking into the brick causing mold, or and that's certainly true in Louisiana, or the freeze thaw damage. So here they are, those joints, in more just blown up a little bit bigger. But again, the concave joint and the V joint shed water the most effectively of the whole bunch, and are most resistant to freeze thaw cycles. On the top of these windows on the left, we're looking at kind of a stone lintel that's been installed, or maybe it's a precast piece of concrete with rebar inside that, but this is a common type of lintel. The other thing we use for lintels could just be steel. And so if you look on the average house, it only has masonry veneer, a 4-inch thick wall that's not really structural. They might have an angle iron plate that's up at the top of that window supporting the brick to span across that window. You don't want just the sheer weight of all that going on the glass. The glass can't handle that. But there's steel angle, there's stone, there's precast, there's concrete reinforced, there's arches, and a bunch of things. The other thing over here you're looking at is the corbelling that can be done up at the very top right corner, where they build up with a bunch of material and have a thicker wall at the top, and it's all about spanning across and around the windows. And then the other thing I'd skipped over was the arch down at the bottom right. And the idea of an arch is you're putting those bricks into compression so that they're, spanning across the window because of being compressed into an arch. And so you'll find a lot of the early Roman bridges and stuff did something on that same principle. Anyways, here they're doing a test of reinforced brick. So this picture that you see at the upper right is two brick walls with an airspace in between that they've poured concrete into. So as they're building this, they would have to tie the rebar and cherry it into place so they have a mat or two of rebar in between. And then when you pour concrete into that space between the two brick walls, you do it on purpose to bond all these ingredients together so that the concrete is bonded to the brick on both sides. It's like you got a fancy concrete form for pouring a concrete wall with rebar inside it. That doesn't get stripped. It becomes part of the look and the strength of that structure. And so, yeah, let's see. So there's that same picture joined up a little bit better. So you could have two mats or walls of rebar in that. You could have more than 4 inches, more than 8 inches thick wall, depending what the strengths you need are. So here's that brick coming out of the kiln tunnel again. The tunnel kiln, whichever way you want to say it. And you can see how some of that brick is brown or darker than others. Yeah, I had an old-fashioned picture at the end I kind of skipped past by accident where it was showing kind of an old simple brick factory from eons before I was around anyways. But things are much more automated now in brick factories, which of course brings the cost down too and the quality up. Okay, well, that's enough of chapter 8 on brick masonry. Our next topic will be on stone and concrete masonry.